Welcome to the optimization class. We are deep in a chapter on convex optimization, and last lecture we have discussed several ways of how to preserve convexity, how to detect convexity of functions and of sets. And I will not recall all of them, but I want you to remember that there is a way to recognize sets and functions and their convexity. Yeah? In particular, one thing of the many things that we have studied, and which I all hope that you remember, is that if you take affine maps, that they preserve convexity of sets, so in both directions. And if you take affine maps and put the result into a convex function, it will also be a convex function. So this is something very useful whenever you have something affine. It basically doesn't change convexity. I will not recall all the other concepts, but what I want to recall is that we introduced a kind of larger class of or a new way of writing optimization problems, which was actually stating for a convex standard form. I recall still. We could say a nonlinear program is convex if it can be written in this form, where you have an objective function which is convex, where you have constraint functions which are affine, and if you have inequality constraint functions which are smaller than 0 for an index set 1 to m. And this problem is convex if f0 up to fm are convex. And that's probably the easiest way to be sure that you've formulated a convex problem. You just make sure that all your equality constraints are linear, otherwise you're lost usually in convexity. That you make sure that your objective is a convex function and that all your inequality constraints are convex functions which are smaller than 0. So that smaller than 0 is important. If you would change the sign here, it would not be convex. Yeah? So the other sign is not convex for general functions. The only exceptions are affine constraints. If these functions fi are linear, if some of them are affine like these, you could switch the sign because they are both concave and convex. A linear function or an affine function is both convex and concave. Okay, so these were the things, and then we introduced some example. You remember maybe what is a QP? A QP is something where f0 is quadratic, and where f1 to fm are affine functions, and then you have what we call a QP. And of course, this quadratic function should be convex. And then we introduced another class which was a QCQP, and that was just f0 up to fm are convex quadratic. Of course, there exist also QCQPs which are not convex, namely when this quadratic has an indefinite matrix. But in this case, we are much less interested in them, and there exist no specialized solvers for non-convex QCQPs. So usually when people say, I have a QCQP, they imply that it's a convex one. Same for QP. So you have to specifically say, I have a non-convex QP, and then people will understand. But usually QP, we assume it's convex. Okay, we already saw some other convex sets which we could not describe with this type of standard inequalities, and one of these was given by matrix inequalities. And I want to, as promised, I want to explain briefly what we call a semi-definite programming problem, because also a lot of interesting problems can be formulated using semi-definite programming. So we are in section 3.6 about semi-definite programming. And the abbreviation is SDP. And YALMIP, the language that we use at the moment for formulating problems, was originally written in order to formulate and solve SDPs efficiently. So you remember that we defined something that was basically a sum of matrices, symmetric matrices, B 0 up to bm, or let's go it until n now. And if these matrices are just some symmetric matrices, and each of these matrices is weighted with a scalar x, which is one of the components of our decision variables, and we require this matrix to be a positive semi-definite matrix. Yeah, that's why it's a positive semi-definite programming, because we have a positive semi-definiteness constraint here. Then we have a constraint which together, this is linear, and it has a matrix inequality, so this is called a linear matrix inequality. Inequality, and abbreviated LMI, we mentioned that already. If you have such a constraint instead of the inequalities, then we say we have an SDP. So what does a general SDP look like? A general SDP looks like an LP, so it has an objective function and it has a decision variable x, linear objective function, and then it has a linear equality constraints. So until now nothing new, but then we replace all the things which were before inequalities by an LMI. So we have B0 plus the sum of xi, bi, I from 1 to n being positive semi-definite. And of course these matrices B, I didn't specify the dimensions, but the only thing we know is that B I are element in the space of R, K cross K matrices and symmetric. That's the only thing we require on them. And the dimension of these B's could be incredibly large, and in fact one can formulate every SDP in this form. If you have several LMIs, several of these, you can actually bring them together into one by using some of the diagonal blocks. Yeah, so you could, in principle, just make one big LMI out of 4 by having blocks stacked together in all these matrices B. Because they get all treated separately, and positive definiteness of the whole matrix when it has this block diagonal structure is equivalent to positive definiteness of each of the blocks separately. That's why actually it's enough to have one big inequality here. One particular form of blocks would be blocks where you have just one element. Yeah, so think of such a thing. So if you just have one element blocks, then actually each of these one element blocks corresponds to one linear inequality, like the ones that we had before in linear programming. So you can easily see that linear programming can be brought into the form of semi-definite programming. So this is an SDP. And it's a fairly general class, easy to write down, and extremely powerful in formulating a lot of problems. So one can show not only that LP, but also that QP, LP, QP, QC, QP, and there's another form of programs which involve second order cone constraints, the second order cone programs they are called. I will not mention them, but they are all SDPs. So basically you could, if you would have a nice solver for SDPs, you could solve all these other things efficiently. Maybe not as efficiently as with a dedicated LP solver, but still using the fact that it's a convex optimization problem. So that's why people found SDP a very exciting development. Of course, the more exciting one is not only that it allows you to formulate all the other problems as form of an SDP, which we only discussed briefly for LPs, but you can do it for all the others as well. But of course, even more exciting is that you can solve some problems which you could not formulate before with this class of semi-definite programming problems. And so let me just give you one example. We will have another example in the exercise on Friday. And so the example I want to look at is the example of minimizing the largest eigenvalue. So It's some problem that sometimes arises in stiffness optimization when you want to have a structure which is, so to say, as stiff as possible. Or it could come in some other applications, but sometimes you might have the problem that you want to minimize the maximum eigenvalue of a matrix, which I call here, I call it G of X. And you want to optimize over variables X and Rn. So this could be an optimization problem where we want to have G of X actually of this form where we have B0 plus the sum of Xi's times Bi's I from 1 to n. And these are also symmetric. That's an important condition. We need, or in order to be able to solve it with convex optimization, we need to restrict ourselves to matrices which are symmetric. But if they are symmetric, then we know the eigenvalues all exist. They are real, and now we could ask a question to minimize the largest eigenvalue, which is a very typical thing. No? And this optimization problem can be formulated as an SDP. So this is like different to write down, and you would even like, if you just think of how would you do it in MATLAB, you would probably call the function eigenvalues, right? So that gives you this list of eigenvalues. Then you take the maximum of these eigenvalues, and that's then your objective function. It sounds like a terribly non-smooth function, and it is actually, if you would just solve it like as if it was a function. It's not differentiable, and it's not nice to optimize, but you can formulate it as an SDP, and then you can actually solve it efficiently and nicely. And the way how to formulate that as an SDP, to give you this example, is that we actually require this matrix to be smaller in the metric sense than some unit matrix. So we will actually solve the optimization problem instead, where we say we want to minimize some factor that I call alpha, which is just one extra variable in the real numbers. X remains a decision variable. So this is a linear objective function, like this. And then our constraints will be that alpha times a unit matrix of appropriate dimensions should be bigger in the metric sense than this matrix, so we can subtract B0 and the sum of all these Xi's times Bi's. And what we see now is also here the alpha enters linearly. It's multiplied with a symmetric matrix, namely with the unit matrix. So this is just one of the summands of the sum. This is the affine part, which we had here, because it's by accident also called B, but of course the meaning of B and X is different here and there. We have an extra variable, this alpha. But we still see that all this is linear, and this should be bigger than 0, and that is now an optimization problem. I make a box around it again. A nice optimization problem, which is an SDP. And what this constraint makes sure, it makes sure that the alpha is bigger than the largest eigenvalue of this matrix. But bigger doesn't mean equal, right? But now we minimize the alpha, and because we minimize it, the optimizer would have full freedom to push this alpha as much down as it likes, but it will be pushed down as much as possible so that it makes this actually equal to the largest eigenvalue. And alpha is in this context called a slack variable. Slack variables are a typical tool in optimization formulations, where you increase the dimension of your problem, you add something like a new freedom, and you restrict it with some new constraints. In this case, is a matrix inequality, in order to get a better and very often a smooth formulation out of a non-smooth one. So this was everything I wanted to say already about SDP. It's not the focus of this course, but I wanted you to know about a lot of optimization problems, and I didn't want you not to know what is an SDP because it's such an exciting thing, and you might meet people that talk enthusiastically about SDPs to you, and then you should at least have a glance of what it is. Okay? I should say that tools to formulate SDPs are YAML in particular. There is also another tool called CVX, both are MATLAB based, and others. And these are not solvers, but these are usually formulation tools, and then there's also solvers. And a famous solver is called Sedumi, another SDP-T3, and there are many others. Just wanted you to know. I think what we will do is we will use YAML and SDP-T3, if I'm not mistaken, Dimitris. Yeah, SDP-T3 will be the standard solver, I guess, that we recommend you to use. Good. Okay, so in this course you will just solve one SDP, and then we go over it. You might, or some of you might want to come back to SDPs in the project later. So that's all about SDPs, so you have an idea what it could be. And we continue with the next section, which is still about convex optimization, but which is actually helping us to compute optimal solutions, or to recognize that we have an optimal solution. So this next section is about an optimality condition. For convex optimization. And you remember what we derived already was one interesting theorem, namely that for a convex problem, a local minimum is also a global one, right? So that was already the main important result. But there is another and more computational result that actually looks at the derivatives of our function, and the wonderful thing about convex optimization is that basically if you just evaluate the gradient of your function, it will tell you already if you have a global optimum. For an unconstrained problem, this will be very clear, so you just set the gradient to 0, and then you have the global minimizer of your convex problem. But we want to make it a bit more general, so let me just give you a theorem which gives you first order sufficient and necessary optimality conditions. It's called theorem 3.5, and it's a first order condition for optimality. I sometimes call it first order sufficient condition for optimality for convex problems. And so what we will do is we regard a convex problem and the problem we regard is minimizing a convex function. I write it in this rather standard form again, subject to x in R, in omega. And omega is a convex set, f is a convex function. Then we also make one assumption, and this assumption is with f element in C1. So f is continuously differentiable, at least on the set omega. And then the point x star is a global minimizer. This is now an if and only if condition, so we can if and only if. I will very often abbreviate it with two f's, if and only if. For all y that are in the feasible set, the gradient of f at x star multiplied with the distance of f of y to x star is giving you a positive number. So that's our optimality condition for convex problems. And you see it's nearly local. It involves only the gradient of f at our point, and then it also indirectly depends on the geometry of our convex feasible set, which in the simplest case is, of course, just the full space. And then this condition would just mean that the gradient should be 0. Let me first prove it. And what we want to do first is this direction. So if this condition holds, then we have a global minimizer. So what do we know about a convex function which is continuously differentiable? We know this first order characterization of convexity, and what was it? It was saying that f of y, so if we have a convex function, that was also one assumption, right? F of y would be bigger than the first order Taylor expansion at any point. Which is this. So this holds for any 2 points x and y, because it's a convex function, and now we can actually take our point x star here, and then we nearly have it, because due to our assumption, this thing will be bigger for every feasible x, for every feasible y, so for any other feasible y, and then this is bigger than 0, so this whole thing is bigger than f of x star. And that is exactly what we wanted to prove, namely that f of y for any feasible y is bigger than f of x star. So this direction is already proven. So we see very quickly, just using our characterization of convex functions, we get a global optimality certificate. That's already the most important condition. Huh? So if this holds, you know you have a global minimizer. Let's just for completeness also go the other way around. So is it also a necessary condition? So first order sufficient, we have proven. First order necessary condition, it is also. So let us see. And what we will do here is actually assume, so for this direction, assume that there exists a y element in omega with f of y being strictly smaller than f of x star. That's contradicting global optimality. And no, sorry, this is not what we wanted. That's what we will have to prove. Let's assume that we have a y in the feasible set where this certificate is not holding. So where this thing is strictly smaller than 0. So we have a point which doesn't satisfy this condition, and then we have to show that there exists a better point, so it cannot be a global minimizer. And then we have proven the other direction. So let's just construct that, and what we will do here is actually we will regard the line between x star and y. So we regard the function on a short line, and we know that this is given by just using normal Taylor expansion by the gradient of f of x star transpose y minus x star times t plus some error which is little o, because it's a C1 function, little o of t. That means in particular that if you make t small enough, this term will dominate that one. And that means that the whole thing will be smaller because that's a negative term, and it will be dominating that one. This thing can be smaller than x star for t bigger than 0, small enough. So when we make our t very small, this will be the case. And that means already that we have found a better point, because this This is a feasible point. It's on the line between y and x star. Both are feasible. So we have found a non. So we have proven that f of x star is not a global minimizer. So in that sense, we have proven both directions. I think that I have forgotten one thing here. The other condition, which I implicitly assumed all the time, is of course that that x star is a feasible point itself. That's something I've forgotten here in the statement, but I implicitly assumed it also in the proof. So this is a C1 characterization of optimality, and of course we, as I said already, we can easily specialize that to the case where we have the full space a solution. I call it a corollary. For omega equals Rn, we have the problem minimizing f of x. That's the unconstrained optimization problem. And our necessary and sufficient condition for optimality is x star is a global minimizer, is exactly equivalent to the gradient of f at x star being 0. And because it's a full set, I don't even need this condition that it needs to be part of the feasible set itself. So this is a very useful and strong result. You might find it not so surprising. You have seen such things very often, but this is about global optimality, and it's only due to the convexity that we could now really prove that this is a global minimum. One example, and the example is an unconstrained quadratic. So what we look at is the minimization of a linear function plus a quadratic part in Rn. And I assume that B is a positive definite matrix. And so the gradient of this whole thing, this function I call f of x. So what is the gradient? Nabla f of x is, of course, c plus b times x. And now that we have this condition, it's an unconstrained problem, we can just set this to 0, and we see directly that x star must be minus b to the minus 1 c. And interestingly, we can now plug this optimizer into this function, which is an exercise I want to do once, because it's interesting. In order to compute the optimal function value, I mean, this is in most cases already the thing that you want to know, namely now you know what is the optimal solution, but sometimes you would also ask what is the optimal value. And so still in this example, continued, we will now look at the objective function. So what is f of x star? So the optimal solution itself is actually c times x, but x is minus b to the minus 1 c, and then plus 1/2, and then we have here an x minus b 1 c transpose b and minus b to the minus 1 c. And beautifully, these minus signs of course cancel, and then also this b and this b will cancel, and that one will survive, and then we have 2 times the same term. So what we have is minus c transpose b to the minus 1 c, and then here we have actually plus 1/2 c transpose b minus 1 c. And you see that it turns out that this is just double of that. So the whole thing is minus 1/2 c transpose b c. So one thing to remember, because we sometimes use it, it's a useful identity which I would like you to remember. And this identity is that the minimizer, or the minimum value of C transpose X plus 1/2 X transpose B is equal to minus 1/2 C transpose B to the minus 1 C. This sounds a bit strange. We had no minus sign here, and here is suddenly a negative number. Also, you might find it strange that here we had a positive definite matrix. Now, the inverse is also positive definite, but then with this inverse, this gets a negative matrix in C. No? We will come back to that. But what I would like to illustrate here is actually an illustration of that theorem so that you can remember it easier. So you have a function. This is f of x. This is x. At the point 0, this function is 0. And then depending on the sign of our gradient, let's assume the gradient c is negative here for a moment, our function will look like this. And obviously here is the minimum. And that is minus 1/2 C transpose B to the minus 1 C. Yeah, so it's very intuitive that the optimal point must be negative because we started our function so that it starts at zero, and so it will go down somewhere. Okay, that was only one example where we used it. We will use it in many other contexts as well. So convex functions which are minimized on the full space are something that we like a lot because it's extremely easy to solve. And the only thing that you need is to invert the equation system that sets the gradient of the function to 0. So as long as you can solve that easily, you have solved your optimization problem to global optimality. I should already say that the only case where you can solve it with easy linear algebra is actually this case, where you have just quadratic programming, because only in that case the optimality condition becomes a linear system in X, so you can work with matrix inverses. In other cases, for more general convex functions, it will be a non-linear condition, and then to find the root of that is a bit more involved. But still, because it's convex, once you have found such a root, you have found or even the global minimizer. So it's a very useful thing. That was everything I wanted to share with you on convex optimization. That was fast. I should say that there exist classes that are only dedicated to convex optimization. We did it in 1 week, basically. But you could follow a full semester or even several semesters only convex optimization, convex analysis. And I can recommend very nice online lectures, which you can just watch as video lectures by Stephen Boyd at Stanford University, which gives a very nice and accessible overview over convex optimization in many of the concepts that I mentioned and many more. So in case you're interested, I can recommend that. By the way, there is also the book by the same author, Boyd and Vandenberge, which you can download freely from the internet. So that's a very nice book that I also recommend you. It's thick like this, and I think the University Library in Engineering has several of them ordered. I ordered them at some point. And if not, you should ask. If you don't find one and you want one, ask them, they will order it. But if you don't need the book as a full book, then you can just download the PDF for free from the internet. So that's also possible. Yes. So more info is first of all the book, Boyd and Vandenberge. The book is called Convex Optimization. And it's let's say, the main engineering reference for convex optimization. It's very accessible and not, not leaving out necessary mathematical details, but it's not too mathematical, let's say. There exist much more mathematical textbooks on convex optimization. One which is also very often cited and which was one of the early books on convex analysis is Rockefeller. Also, I think, convex optimization. And what I also wanted to say is there are Boyd video lectures. And this is something that I met a lot of people that watched them and liked them. And so it's a very charismatic teacher also. This is everything I wanted to say about convex optimization for now. And I want to go on, because we have a lot of things that we want to cover in this course. And I want to conclude the part on foundations and basics that we are still doing at the moment with a chapter on duality. So what I want to do is actually something I could also do after the break, because it's a new chapter, so it makes sense that we have a bit earlier the break today. I suggest that we stop here and that we continue at about 3 o'clock and maybe 3 and 5 minutes, and then we continue with the next chapter. So we continue, as promised, with another chapter, and this chapter is about duality. It's some concept that is also fundamental, and it's good to know about it, and it's something that is also very much related to a lot of the arguments that we will later regard. Chapter 4 is about the Lagrangian function. Lagrangian function and duality. And as you might guess from this name, it has something to do with Lagrange, the great French mathematician of, I think, the 18th century. So what we regard as an optimization problem in the standard form that we looked at before. So f of x is what we minimize over x, and then we have equality constraints g of x equals 0 and h of x bigger than 0. Let's write it in this general form again. And of course the function f is a scalar, and g is vector valued, and h is also vector valued. And the only thing that we change is the name. We just call this now the primal optimization problem. Because we want to find another problem which is turns out to be based on the same data, but which will be called the dual. We will also define the optimal value of this optimization problem. That means the minimal function value. We call it P star. So it is f of x star, like this thing. I should say that this notation f of x star implies already that x star is unique, which sometimes it isn't, but the function value itself definitely is unique. So there is only one best function value, and that one we call P star. So that is the primal optimal value. So we give it a name, P star. So what we want to do with duality is actually find a lower bound, some lower bounds on the optimal value. And there is one function which helps us to find these lower bounds on the optimal value. That is called the Lagrange function, the Lagrangian function. So a definition is the Lagrangian function And because it's the Lagrangian with an L, we will also denote it with L, but we will use a curly L so that it's not getting confused with other things. So this curly L is always a Lagrangian function. And it is a function which depends not only on x, our variable on which all these things depend, but also on two other quantities, which we call lambda and mu. Greek letters, but vectors here. And the Lagrangian function is just the sum of our objective function minus lambda transpose G minus mu transpose H. So that's a fundamental definition, so we should keep that in mind. We will use it extremely often, so it's very good that you have this in your memory. We see already from this definition that the lambda and the G must have the same dimension, otherwise this product wouldn't be defined, and the same for the mu and the H, so they must be of appropriate dimensions, namely in the same dimensional space as we had our equalities and inequalities. These lambdas will have arbitrary values in this appropriate real space, right? So x, let's say x is element in Rn, that was the original space. Lambda is element in R, and we called it P in this chapter, I think, and also previously. And the mu we called Rq, and that actually is motivated by the fact that G is element in Rp. So the value of G and Hx is element in Rq. So they are actually functions mapping into the spaces of appropriate dimensions. But now these mu's are usually taken positive, while the lambdas take every value, and this is motivated by a little theorem that I will prove very quickly. So we call it a lemma. And the lemma says, if you have a feasible point, and you have lambdas which are anything and mu's which are positive, then the Lagrangian is a lower bound of f. Yeah? So for x tilde element in the feasible set, so I shorten this to x element in omega, that means feasible, again. Huh? And mu positive, we have that L of x tilde lambda and mu is smaller than f of x tilde. So we have a first lower bound property, and the proof is extremely easy. Why? Because what we have here is actually f of x tilde minus lambda transpose G of x minus mu transpose H of x. So this is so nasty to write. I think I will do it somewhere else. Sorry. So the proof. So what is L of x lambda mu? It's given by f of x minus lambda transpose G of x minus mu transpose H of x. And because we said that it's a feasible point, this thing will be 0. So this whole thing here will be 0. And because it's feasible, this will be positive, every component. And also this will be positive, every component. And so the whole thing here is smaller than or equal to 0 because of the minus sign. And so then we see that this whole thing is f minus something, so that will be smaller than f of x at a feasible point. Quite trivial, but just something that we can prove easily. So this is so trivial that you say, why did you prove it? What we can now do with this Lagrangian function is we can minimize it, and when we minimize it, we know, of course, that we will keep a lower bound to our optimal value, and that's what we will now define. So we will define a function which we call the Lagrange dual function, which will already minimize over all x. So this is not the Lagrangian itself, it's the Lagrange dual function. So this is the Lagrangian function, and that's the Lagrange dual function, and it is defined by, we call it Q, lambda and mu, and I realized when preparing yesterday the lecture that the Q is doubly used here very nastily. This Q is now just a scalar function, which is defined by the infimum over all x in the space of our Lagrange function for fixed lambda and mu. So you just fix lambda and mu, some values, then you get this Lagrange function, and then you say I minimize it over all x, and by minimizing over all x you got rid of x because x is now minimized away, and you get a function which only depends on lambda and mu. And this Lagrange dual function is a very interesting function. What we would easily have, for example, is that the following lemma. If the mu is bigger than 0, then, of course, for any other value of lambda, it doesn't matter what lambda is, then this Lagrange dual function, because it minimizes over all possible x, it can only be smaller than p star. So it can only be, it's a lower bound already on the optimal value for any. Yeah? So you just pick some lambda and mu. The mu should be positive, that's the only thing. But then you know that this Lagrange dual function is already a lower bound to the global minimizer of your optimization problem. And of course it's a consequence of this property. So for any feasible one, so when you take some feasible point, so for any feasible point you have, maybe let me just prove it formally, proof. For any x tilde in omega, we have of course that q lambda mu is smaller than f of x tilde, right? Because the Lagrangian function is smaller at that point, and then you minimize further, it can only become better than the Lagrangian function at the specific point, so it must be smaller than f of x tilde. It's just this inequality a bit further. And now this will in particular also hold for x tilde equals x star. And then we have it. Okay? Only in this case. So this is already something interesting. So now we have a function which does not depend on x anymore, which in some cases we will see we can explicitly compute, and which gives us a lower bound on the optimal function value. So this is very interesting. One thing I should say, and which I didn't say at the beginning, is that the optimization problem that we regard is not necessarily convex. So it's not necessarily convex. It can be convex, also then all this holds, but it need not be convex. It just can be anything. One very interesting thing about this dual function is now it turns out that this dual function is a concave function. It's always concave. So there is no other, just by definition of this whole thing, it will be a concave function. This is something I want to prove. It's theorem 4.3. And it just says that the function q, which is a function from Rp cross Rq, and here you see how ridiculous my notation is. I have q 2 times in 2 different contexts. But anyway, it will be recognizable from the context what it means, right? This function q is concave. No matter what the functions are. And the proof of this is using our convexity preservation rules that we have studied last time. And let me just, it's a concave function, of course, in the variables lambda and mu, in its arguments. And the proof is as follows. I think the formality of this proof is, I will use a minus sign here, but I think before I do the formality, I want to give you the intuition of that proof. So first, let's make a picture. And the picture is this. If you have here lambda and mu, and of course only one component, so assume some lambda or mu, and you regard what the Lagrange function looks like, then for every fixed x, for one x, the Lagrange function, because of its definition, is a linear function in lambda and mu, right? So when I fix x, then it's a linear function in lambda and mu. So basically, this is L of x1, let's say, for x, some x, lambda mu for x fixed. That's just a fact, because it's by definition linear in this lambda and mu. Now I take another x, and I will have a different value of my Lagrange function and also of g and h. So I will have some other thing here. So this will be a different x, just for another x. And I can draw it for many, many, many x's. Another x. Another x. Another x. Okay, so for any x that I could choose, I could draw the Lagrangian function, and it will always be a linear thing. And now what was the definition of the Lagrange dual? It is the infimum over all possible x's. So for a fixed lambda and mu, it would take the infimum of all these values. So that's not this might be. Actually, there might be something else, because there might be another x. But you see already that the infimum will be the thing here below all these cutting planes. And so we get actually a concave function. And that's exactly the application of this supremum of convex functions, which is convex. And that's what we apply, but it's with a different sign, because here we don't take the supremum, but we take the infimum. So what we see is actually that minus q of lambda mu is equal to the supremum of minus L of x lambda and mu over all x. Yeah? So I just put a minus sign to make from minimization a maximization. And these things are linear functions in lambda and mu for every single x. That's the main point. X is now an index and not a variable anymore. But if we take over all possible x's the supremum of this, so these are actually affine functions, and this means affine, thus convex, in lambda and mu. So you have actually convex functions in lambda and mu. You take the supremum of convex functions, so sup of convex is convex. That's something we have actually proven last time by the intersection of epigraphs. So minus q is convex. Minus q is convex, which means that q is concave. So we have magically somehow transformed our original problem into a very different problem, which gives us not a different problem. We have now actually a function q which gives us a lower bound on the optimal value, and at the same time we know this function has a nice property that it's concave. Concavity is a nice property, of course. So now the next question could be, if we know that this concave function is an underestimator of our optimal value, maybe we could maximize that function. Maximizing a concave function is a nice problem, you remember? So would that still be a lower bound? I think yes, because whenever we would maximize this function over lambda and mu, and we make sure that mu is positive, for every single value it will be smaller than p star. So what we will get is that even if we maximize over all possible lambda and mu, we would have a positive, a lower bound of our dual value, of our primal value. So maybe I make a bit of space here. And so this actually already defines our dual problem. So the dual optimization problem is just the problem where we say, let's maximize this function q, lambda, mu, subject to the constraint that mu is bigger than 0, where lambda is in our P and mu is in our Q. So this is an optimization problem, and it has an optimal value, and the optimal value I will denote by d star, the dual optimal value, and d star is of course the value of Q at, for example, the optimal multipliers if we have them. So it's this value. You can actually use this max because that max itself is giving you back the optimal function value, right? So that's why we can write an equality here. And what we have here is the dual optimal value. And of course, by this construction, because we optimize over all possible lambda and mu's, where we make sure that the mu itself is positive for each component, we have already the very interesting property, which is a theorem. We don't need even to prove it. It's called weak duality. And it just says d star is smaller than p star. So by maximizing over the lower bounds of our optimization problem, we will of course keep a lower bound. So it's just the best lower bound that we can get from our Lagrange function, from our Lagrange dual function. So this theorem is already basically proven. And it's something that allows you to transform something which is in variables x into something which is in completely different variables, namely lambda and mu, which only involve the constraint functions. And of course it relied on one crucial thing, that's the definition of this Lagrange dual function up there, where we had to minimize over all x's in order to get rid of the x's. And this is sometimes easy and sometimes not so easy, but it's something that in theory we can always do. So that's already quite a funny and interesting result, I would say. And now I want to go further, and from now on I will not prove anymore. Because this is not the main topic of this course, but it's something that which is still very important for you to know. And this theorem is actually a stronger version of this. The next theorem is called strong duality, and it basically holds for convex optimization problems. For convex primal problems, and it says, if this optimization problem. Yeah? If the primal is convex and it satisfies a so-called, it's a technical condition. This is called Slater's condition. I will mention it and satisfy Slater's condition. Then D star is equal to P star. So that means not only is it a lower bound, but it's exactly the optimal value that you get by solving the dual. So that's a much stronger result, and that's why it's called strong duality. As I said, we will not prove it now, but I will at least tell you what the Slater condition means so that you don't feel that there is a gap. This Slater's constraint qualification, I specify here. That's maybe more, it's a technical condition, but I want to make sure that we have it. For a convex problem, what do we know actually? Because it's a convex problem, we first of all know that g of x will be equal to ax minus b. Yeah, so it will be an affine, otherwise we don't have this convex problem, right? And h of x, hi of x, will be a concave function for I going from 1 to q. And q is now again the index, the number of, yeah, so this is not yet Slater's condition, but it's just something we should keep in mind. So that's because it's a convex thing. And what Slater's condition says is that there must be a feasible point for the primal problem, which is satisfying all the linear constraints, also the linear inequalities. And if there is a nonlinear but convex inequality, it should satisfy it with strict inequality. That's a bit more than just saying there is a feasible point. Yeah? So it's an extension. Slater's condition says there exists a feasible x. But not only should it be feasible, maybe I call it x bar, with hi of x strictly bigger than 0 for all nonlinear inequalities. Because they can be convex but nonlinear. Like, for example, in a QC, QP, you had these convex constraints. But if you have a curved, and I is the index of the nonlinear inequalities. Yeah, so for any nonlinear inequality, it should be positive. So if I just draw an example, I want to give you one example so that we get a feeling what this is. So imagine you have one constraint that says h of x, I call it h1, that's the first constraint, which says that I have a concave function, let's say x1 square, the minus sign, minus x2 square, plus 1. Okay, this function is actually describing a set, namely a circular set in the two-dimensional space, right? And all the points in the middle are feasible. And now I could have other constraints, let's say h2 of x could be, for example, just x1. And if x1 should be positive, then this will cut out everything here. And I cut it already out, all this part. So the remaining feasible set is still this set. And now I could do something nasty. I will just add another inequality, namely h3, and that is minus x1, just to make it a bit nasty. And now I will get, I cut away everything on this side. And now I have basically removed a lot of things, but the only feasible set that remains are these points in the middle. And what Slater's condition says is, now I want to have at least one point which satisfies the nonlinear equality, namely this thing, strictly. So I have an interior point, so I'm really in the interior. And so this would still satisfy Slater condition. There is a feasible point. But if I now would do something really nasty and I would add some other constraint, namely another curved constraint that, for example, cuts out all the points which are below this parabola. So I would add another h4 of x, which says that x2 should be bigger than than 1 plus x1 squared. So this would actually make sure that the x2 must be above this parabola. Then I immediately have only one point left. This is the only feasible point. It's a feasible point, but both the this and that parabola, they will touch, and so there is no feasible point in that strictly satisfies both the nonlinear inequalities. So without it was still satisfying Slater's condition. With this, it will not satisfy Slater's condition anymore. Yeah, you see already that these will be quite degenerate problems when you don't have this Slater condition satisfied, and in most practical cases we will have it satisfied. So it's a rather technical condition, but for completeness I wanted to state it, so that you at least know when this theorem that we call strong duality, when does it hold. But in order to illustrate how duality can be used a bit in practice, or what we can do with it, I want to formulate already the dual of a QP. And I use a strictly convex QP. I forgot actually to define what is strictly convex. For a QP it means that all eigenvalues in the Hessian are strictly positive definite. And for a general convex function it means that whenever you take a point intermediate, that it's actually strictly bigger than the function value. Yeah? So it excludes completely flat functions. So actually I should define it, just for completeness. Strictly convex means for all x and y, and so an f from omega to r is strictly convex if for all x and y in omega you have, and for all t which are in the interior of 0 and 1, that's the important difference now, you're only looking at the interior points, then f of x plus t y minus x is strictly smaller than f of x plus t f of y minus f of x. So this is just a little box which I wanted to add for completeness. It's not the topic of this, it's just so that we know what I mean when I say strictly convex. Yeah? So here's the difference to the usual definition are these three signs. So it's only the interior t, so it's not this point and not this point because they will be equal. It's all the interior points and they should be strictly bigger. Okay, and a strictly convex QP is of course a QP which doesn't have a, that means that the matrix B should have positive eigenvalues only and no zero. And so now what we have here is the primal problem. P star is equal to the minimization of x of a function cx plus 1/2 x transpose bx subject to, and I add some equalities, ax minus b equals 0, and I add also inequalities, big cx minus d is bigger than 0. So that is my primal optimization problem, and it is convex. And I want now to compute, to get a bit of experience with these dual functions, I want to compute the dual function. So let's first define the Lagrangian itself. So what will be the Lagrangian? X lambda mu. It will be the function that consists of the objective, C transpose x plus 1/2 x transpose bx. And then I subtract the equalities lambda transpose ax minus b and the inequalities mu transpose cx minus d. Do you all agree? That is just the definition of the Lagrangian function. And now I reorder these terms a little bit. Still the Lagrangian, so that everything that appears with an x is a bit isolated. And everything which is not appearing with an x is separate. So there is not an x with this lambda times b and this mu times d. So what we will have first is lambda transpose b plus mu transpose d. So these two things are completely independent of x. And then the remaining terms are all depending on x. And some of them are linear, like this is a linear term. This is a linear term, this is a linear term, and this is a quadratic term. So what we will still have is our old quadratic term, x transpose bx. And we will have our collection of all linear terms, and I will collect them so that we have the x on the right side, like here. And then I will add a vector here and put the transpose at the end of this vector. So then I can collect the c here, that was one part. And then I have here a minus, and lambda transpose A is multiplied with x. So with the transpose, it's actually A transpose lambda with a minus sign. And here I have the same minus C transpose mu. So now I have just reordered my Lagrangian, but why did I do it? Because this will allow me to compute very easily the Lagrange dual function. So what was the Lagrange dual function? Q lambda mu was the infimum over all possible x of our Lagrange function. And we have an explicit statement of our Lagrange function already, and we see that it has something that is constant in x, something that's quadratic in x, and something that's linear in x. So the constant part I can just copy. It's not affected by the optimization. But now comes this and that together, and here I can apply this little result from before the break that I said, please let's remember that. Namely, we have an unconstrained quadratic with this term and with this term. So it will be, this is the gradient here, and this is the quadratic, and you remember it was, even this comes with a 1/2, so everything is nice. This will be minus 1/2, and then the gradient, b to the minus 1, and the gradient again. That was the result from before the break. And c minus a transpose lambda minus c transpose mu. And here we have the same. A transpose lambda minus c transpose mu. Now we have an expression that is explicit for our Lagrange dual function. And we could reorder this if we like. And I think it makes sense to reorder these things again a bit more. So I will just have q lambda mu. What will it be? It will be a function which is containing, now I'm interested in this function as a function of lambda and mu. So it will contain some terms which are completely independent of lambda and mu, namely the c and this c. And it will contain some quadratic terms in lambda and mu, and it will contain some linear terms, these ones, and also the mixed term c mixed with this term. Sorry? So here's something wrong, or where?
transpose?
Oh, here's a transpose missing. Thank you. Wonderful. Yeah, absolutely. So let us reorder these terms a bit, and I will just put out the constant term first because it's the most boring term. So I have minus 1/2 C transpose B to the minus 1C. Then I will collect the linear terms, and I want to collect them directly in a form where I have lambda and mu as a vector, because they will be the optimization variables of the linear of the dual problem. And then I have here the B and the D. So I will have a vector here plus, I make it already a bit bigger, I make a transpose here, and then I have a B and a D. And these two things will be multiplied with lambda and mu, and then we get already these two terms. And now I want to get the cross terms from it. And what are the cross terms? So the cross terms are actually where let us, for example, regard this term. So here we have a B to the minus 1 with a C, and then it's with a minus and another minus. So a plus with A transpose lambda and C transpose mu. And so we can actually see that we will have the terms which are with a plus sign. The one with a lambda comes with an A. Sorry, the last term here is the A. And for the mu, the last term here is the C. And then they get multiplied with, here's a transpose, another transpose, so I got rid of them. And here I have a B to the minus 1 in front of both and a C. So these are the linear terms. And they are here with a minus 1/2. The minus sign I got rid already because of the double minus, but it's a 1/2, but it appears also twice if I make this product. So I have all the linear terms, and now the only thing that's missing is the quadratic part. And here we see that the quadratic term is actually B, and then times this interesting matrix here, which I will write down as follows. I will just write it like this, B to the minus 1, and then I have one matrix which is A and C, and here's the same matrix, A and C, not transposed. And I have here my minus 1/2 and lambda and mu, transpose and lambda and mu. So basically this product gives you A transpose times lambda plus C transpose times mu, which is this thing. Then I multiplied with B to the minus 1 and then the same transposed. And I got rid of both the minus signs because they are the same, and then the one minus sign in front is remaining. Okay, so that's just quadratic multiplications. And now I have an objective function, and the dual optimization problem will just be what will be the dual optimization problem? It will be maximizing Q, lambda and mu. Did I say maximizing? Yes, just to be sure. Over all lambda and mu, subject to mu bigger than 0. And of course I could now copy this function, but this is clear, right? So what we see is this is a QP again. Convex QP. Okay, I call it a convex QP. You might say, no, this is not convex, this function is concave, right? But of course it's a convex function. It's a concave function that I maximize, so it's equivalent to minimizing a convex function. And one thing that I want to point out here is we proved already that this dual function is, where did we prove it? So this thing, theorem 4.3, that Q is a concave function, we have proven it. But we see now, if we look at this function, what is it? It's a constant, it's a linear, so that's by either convex or concave. But this thing is a positive semi-definite matrix, right? It's a matrix that's positive semi-definite. and it's this matrix here, it ends. Yeah? So this whole thing is a matrix. And it's multiplied left and right with our lambda, so it's a quadratic function, but it comes with a minus sign, so it is a concave function. So this whole thing is indeed concave. So we see that it's not only just in this theorem that it's a concave function, but we see already by just doing the computations, going through our definition, doing a bit of basic mathematics, we end with a concave function, like we have proven before. So if you would see this QP, it's in variables lambda and mu, completely different than the original one, which was in variables x. And you see that also the locations of C and B and A and D and so on, they are intermixed at very different places. But because of strong duality, we know that this value, D star, is equal to P star. So we know something nice. Do you still digest? Are you still able to digest one further example? Okay. So I want to give you a second example, which is maybe it has a catch, but it's actually a simpler problem. So we make now a dual of a. So it's the next example. It's the dual of an LP. So it's a simpler problem. We actually drop this term here, but it makes our dual function optimization a bit different. And you will see in a minute. So the Lagrange function will be, of course, exactly the same as this thing, but this term will not be present. Basically, it's just the same as before, with b identical 0. So we can actually go through the same computations, and we will see that L of x and lambda mu is given by this expression here. So it's lambda transpose b plus mu transpose d. Here I forgot actually that there is a plus sign, right? Plus c minus a transpose lambda minus c transpose mu transpose x. So that is now our our Lagrange function. And now we get the little problem. When we define q of lambda and mu, it will be the infimum over all x of this function. Over all x, unconstrained. And so what you immediately see is that this term is of course constant, so it doesn't really matter, right? But this term is nasty. Because if this thing is some vector, any vector that is non-zero, so if this is just not 0, then you can always choose an x that is making this whole term minus infinity. So when you minimize, you will always get minus infinity whenever this is not 0. So what you will get is actually this thing. I will omit maybe x lambda mu. This will be either minus infinity if c minus a transpose lambda minus c transpose mu is not equal to 0. And otherwise it will have this finite value lambda transpose b plus mu transpose d else. So we have a function, this Lagrange dual function has minus infinity values, and minus infinity is of course not a nice number. On the other hand, we maximize. So what will be our dual problem? It will be something where we maximize. And like plus infinity means infeasible for a minimization problem. You remember this epigraph formulation, yeah? Plus infinity is basically infeasible for a minimization problem. Minus infinity means infeasible for a maximization problem. Yeah? So we can interpret minus infinity means infeasible for maximization. And so this all is based on our epigraph formulation. So what we can now do is we can formulate our dual problem either like this, max of q of lambda mu subject to mu bigger than 0 over all lambda and mu, and then we take into account that this q is sometimes minus infinity and that we should avoid it. But a maybe cleaner statement would be that we directly make these minus infinity values, we avoid them by having this constraint, and we just say let's maximize the function that we have, namely lambda transpose b plus mu transpose d, and we have lambda and mu, and instead of only having this constraint mu bigger than 0, we now also have this constraint that the other components should be 0, so Ca transpose lambda minus C transpose mu must be equal to 0. So I've just made this constraint that was implicit in my function q by making infinite values. I made it explicit by just adding it as an equality constraint. And so whenever this condition is satisfied, this is the right value of q, and when it's not satisfied, it will not be the optimal value anyway, because it's minus infinity. So these two problems will have exactly the same solution, and that is the dual problem. And that's the way that we can actually state it. And now let's look at this problem again. It's a maximization problem. It has a linear function in lambda and mu. It has linear constraints, linear equality constraints. So which class of problems does it belong to? It's another LP, right? Again, an LP. So the nice thing is for strictly convex QPs and also for LPs, we get that the dual problem is again in the same class. Interesting. And it looks very different. So if you think of what was the original problem here, it would have been actually like the QP, but with a zero Hessian. So the C was in the gradient, and the matrix A and C were there multiplied with an X. Now the A and C matrix still appear in a constraint, but they are now multiplied with a lambda and they are transposed. So, and the B and D, they are now in the objective. They were just in the constraints before, so things changed their place. But still we have this interesting and strong result that D star equals P star. So we can either solve this one or that one, and we get the same value out of it, which in some contexts can be much faster and easier to solve. We will discuss it in the exercises. That's it for today. And next time we will actually finish the foundational part and start also with unconstrained optimization and Newton type algorithms. Thank you very much.